Hi there, everyone. My name is Lucas Curbs. I am the instructor for Math 118. This is section 6. Um, we have a really interesting course that we're going to explore together this quarter. Um, the bulk of it will be studying functions of the real numbers, and we will get into a lot of our definitions of functions and their graphs and all of that, I think starting next week. Um, but before we do that, we need to do a little bit of foundational work. One of the big differences about math at a college level like this, especially here at Cal Poly, is we're a little bit more formal in how we talk about these ideas. And so, actually, before we can even talk about um, functions or expressions, we need to talk about sets. Now, a set is a collection of objects. And that may seem very general, and it sort of is. And we talk about sets a lot. We'll talk about sets of numbers. We'll talk about, well, sets of numbers will be the main thing that we're going to talk about, but I'm going to actually introduce sets in a little bit of a different way. We're going to start by talking about the collection of all dogs. And we're going to label that D, right? And this is how we can talk about sets explicitly. We can say that D, we do this opening brace, is the set of all X. Then we have a colon. And then we say where X is a dog. And as we look at this expression, let's sort of dissect the anatomy of it. We start with these braces, and these braces sort of act as the container. They tell us that the thing that we're looking at is a set. This X right here tells us the object in question. So in this case, we're just looking at something called X. And then there's this colon. There are some places where you'll see this colon actually as a vertical line. The textbook goes back and forth between both. At Cal Poly, for the most part, we use the colon, so I'm going to be using the colon. And this colon acts as a separator. You can read it as saying such that or where. And then finally, we have this thing right here. So if this colon means such that or where, then this underlined thing is sort of the rule that governs the object. The other way that you'll see these sort of written, or sort of like another way to think about these, is that they're written like this, right? Some set S is a set of elements, right? Our X's that are subject to some rule. I can give you an example of numbers, right? So we could have, say, the set of n, right? Some numbers n, where n is even. And this is where these sorts of rule descriptions are really nice, because I can attempt to write out all of the even numbers, but it will take a very long time, right? We can start like this, right? We can start 0 is even, 2 is even, well, but so is -2, and so is 4, and so is -4, and so on and so forth. You get this infinite set. Rather than writing down all of these infinite entries, we can just say the set of n where n is even. Now, if we want to talk about the things in the set, right, we close this bracket here. We have here, we call them elements. And that is the general thing that we call, right? Going back to this set here, right? I have a dog. His name is Augustus, right? We call him Gus for short. And so that I can say Gus is in the set D, right? He is an element of the set of dogs, based solely by the fact that he is a dog. And the symbol we use for that is this little guy here, this little epsilon. Um, this guy means is an element of. So Gus is an element of the set dogs, meaning it is true that the object Gus follows the rule is a dog, right? Further, I can say that Gus is in a different set, right? Gus is in the set B, where maybe we'll say this is the set of all X, where X is a black dog, right? Gus is a black lab, so he is a black dog, right? So Gus is in this set as well. In fact, you'll notice actually that for every black dog, right? Let's just talk about some generic black dog, right? One of the things that marks these college courses as different than the high school ones is a step towards generality. So we can talk about a generic dog, right? So say some dog D is a black dog, right? So some dog D is an element of our set B. Generally, sets use capital letters, elements use lowercase letters. If this is true, well then automatically this dog is also a dog, right? If it's a black dog, then it's a dog. This is a concept called a subset. And a subset basically means that every element of the smaller set is an element of the bigger set. If you want to think of this as a picture, right, we can have this as the set of all dogs, right? And the set of all black dogs might live somewhere here, right? Every black dog is a dog. Not every dog is a black dog, but every black dog is a dog. When this is the case, we can denote that like this, right? B is a subset of D, right? Where this symbol here looks basically like a less than or equal sign, but it's rounded instead of sharp, like that. Next, we're going to talk about three quick set operations. And our set operations are basically ways that we can combine sets to get new sets, right? In the same way that our operations for numbers, addition, subtraction, multiplication, combine numbers to get new numbers. The first one is the union. So I suppose we'll need a couple of sets in order to talk about this. So let's grab some sets of numbers. Let's say A is the set 1, 2, 3, right? It's perfectly valid to skip this whole element rule situation and just explicitly list the elements of the set if that's a thing that we can do. Note we still have these braces because they, as I said, act as the containers to tell us that we're talking about a set. So let's have A be that set. And since we already used B for black dogs, let's say C is the set 3, 4, 5. And the union combines sets to create new sets, right? That's what an operator does. So let's talk about A, and then we use this big U for union, C. And that is a set that we say looks like this. It's the set of all X, where X is in A, or X is in C, right? So essentially this just brings the two of them together, right? So A union C is everything that's in A or in C. So 1 is in A, 2 is in A, 3 is in A and C, but this is not an exclusive or, so it is totally valid. 4 is in there and 5 is in there as well, right? So this combines sets and just gives you basically everything, right? If you are more of a visual learner, if we have some set right here, A, and some set here, C, well then A union C is all of it, right? It's everything that's in either one. The next set operation is the intersection. So I guess I should write that down. So the intersection is sort of similar to the union. We write it instead of this U being up, we actually write it upside down. So A intersects C. And that it starts very similarly. It's the set of all X, where X is in A and X is in C. So what this means is it's everything that's in both of them, right? In this case, that's a set containing one element, just the element 3, right? If we look at our picture, right, we have A, we have C. The intersection, well, is just what the name would say. It's right where they intersect. One thing of note here, this is not the number 3, right? A intersects C is not the number 3. It's the set containing 3. The final one, we won't use this one near as much. We'll talk about unions and intersections a lot, especially towards the middle of the course. But it will come up from time to time, so it's worth talking about, and that is the set minus. So it is slightly less intuitive, but I think you should be able to get it fairly easily. We use this slash. Some people do use a proper minus, but the slash like this is more correct. So A slash C is everything that looks like X, where X is in A, and X is not in C, right? So this is A minus C. Let me actually change this to a brace. And if we look at our picture, right, we have A here, we have C here, and A minus C is everything that's in A minus everything that's in C. So notice that this little part of the intersection is not in this new set. In this case, A not C, back to our numbers here, A minus C, well, it's everything that's in A, but not in C. So that would be 1 and 2. Quick little example that I guess I'll just sort of squeeze here at the bottom. I want to ask you to consider the object. So A minus C. So first do that. That's what our parentheses tell us. Then I want to intersect that with C. Now, if we go just straight to our numbers here, A not C is 1 and 2. Or A minus C is 1 and 2. When I intersect that with C, it's everything that's in A minus C, which is 1 and 2, and in C, 3, 4, 5. So there's nothing. But we can't write that as like the set containing 0, right? Because 0 could be an element. Instead, it's the set containing nothing. And that's a little bit ambiguous. So we tend to write it like this, a 0 with a slash through it. It is the empty set, the set containing nothing. So this is the empty set. And with all of that behind us, with these sort of basics of these set operations, we can actually start talking about these more general sets of numbers and intervals and start building functions. So what are the common sets of numbers that we're going to be working with? So the common sets of numbers there's going to be 4 of them that we will work with throughout the quarter. There's a 5th one that I think we'll introduce later this week, but there's 4 main ones, and they all have special symbols. And so let's take a look at them. So the first one are called the natural numbers. And we denote the natural numbers with this fancy N, right? It's sort of an N with this sort of hollow in the middle. And the natural numbers are simply the counting numbers, right? So 1, 2, 3, 4, and so on. All of the whole non-zero positive numbers. The next set is the integers. The integers fancy symbol is this Z. Don't ask me why it's a Z. I was never able to figure out quite why that got a Z and not something like an I. But but this is the positive and negative whole numbers, right? So we can start at 0. 1 is in there, -1 is in there, 2 is in there, -2 is in there, and so on, right? This is all of the whole numbers, both positive and negative. The next set is the set of rationals. Of all of these symbols, the symbol for the rationals is the least important. Often when I'm talking about rationals, I will just use the word rationals. For completeness, however, it's written as this fancy Q, similar to how there's the fancy Z and the fancy N. And this is our definition. I'm going to write it down, and then I'm going to explain it. So it's the set of P over Q for P and Q in the integers. So that may look a little confusing, right? Before we were just explicitly listing, and now we have a rule, right? But let's break down this element rule pair. Our elements look like P over Q, where P and Q are integers. So these are just all of the fractions, right? These are all of our fractions where we have whole numbers for our numerator and our denominator, possibly negative, right? So 1/2 is in there, 3/4 is in there, -22/7 is in there, and so on and so forth. The next one, which sort of takes a big leap, is the real numbers. For the real numbers, we use this fancy R. This is probably the most common symbol we're going to see. R and Z, these two are the ones we're going to be using the most. And the real numbers are more or less everything, right? As far as numbers go, right? A dog isn't an element of the real numbers. All of the numbers that you're used to working with, right, are in this set. One thing that I do want you to notice, right, the natural numbers are a subset of the integers. The integers are a subset of the rationals, right? Because you can write any element of the integers as a rational, just let Q equal 1. Then those rationals are further a subset of the real numbers. So what else is there, right? Like what sits in between here? Well, this is sort of where our set minus can work, right? The real numbers, set minus the rationals, those are the irrationals, right? Those are all of the numbers that can't be written as fractions, right? Pi is in there, e is in there, the square root of 2, the square root of 3, all of those fun numbers are in there. And the real numbers are sort of the main object of our study this quarter. So let's sort of take a look at how we can talk about or express the real numbers. So there's two main ways that we sort of initially start to think about the reals, right? The first one is by their decimal expansion. And the decimal expansion of these numbers is exactly what you would think, right? It's taking these numbers and writing them as a decimal, right? So you might have the number 3, which is a real number. Now, implied in the number 3, right, is this, it's 3.0000, and on and on and on and on. It's this big, long number, right, that has all of these infinite number of zeros. That's its decimal expansion. We can also talk about, something that repeats infinitely, right? Say, 0.7777, and so on, right? Often just written 0.7 with a bar over it to tell us that the 7 repeats. You could have even weirder ones, right? You could have, 1.01, 02, 03, and so forth, right? These are decimal expansions of real numbers. Now, the other way to think about it is the number line. And I know you all have seen the number line before. So we will go through it very quickly. For the number line, we start with a line, and we just need a single point to center us somewhere, right? Let's call this 0, right? You could have a whole bunch of, like all of the points on this line are real numbers, right? Um, you might have the point -5 somewhere back there. Um, negative pi over 2 might be here. Some of the numbers that we put on the other page, 0.7 repeating would be here. 1.01, 02, 03 could be there. 3 would be there. You might have pi just right after 3. All of these are real numbers. And it just allows us to sort of categorize and look at a big chunk of them. But all of the sets that we've been talking about, right, all of the ways that we've understood these real numbers have been by explicitly listing elements or giving a rule for them. But what happens when we want to talk about sections of this line, right? We don't want to just like list all of the elements in some sort of section. It turns out actually that you can't, right? Let's say we want to talk about this section right here, right? Between -5 and minus pi over 2. It turns out, and this is well beyond the scope of this course, but it is just sort of a fun little thing. There's no way to actually list all of the numbers that are in that little section, that little interval. So we introduce the concept of intervals to do this for us. And there are a number of different ways to represent different intervals. So I will throw down some big dividing lines for us. And we can talk about different ways to express intervals. So here we'll use the interval notation. Next, we'll talk about the set notation. We'll talk about these as sets. And then we'll place it on the number line. And I'll move that over just a little bit, right, to give us a visual representation of these objects. So the first sort of set that we're going to talk about is sort of what we did here, right? Let's say we have the set between A and B, right? Where for all of these, we're going to assume that A is less than B. And what that is, if we draw our number line, let's place A, let's place B. That's everything, that's A, and all of the stuff between it and B, right? One of the things of note is that we filled in these endpoints, right? This is the closed set, the closed interval AB, right? Where we include those endpoints. As a set, we can write this as the set of all x, where A is less than or equal to X is less than or equal to B, right? This sort of formalizes the equal part, right? Like A is in this set, B is in this set. To sort of contrast this, we might have the open interval AB, right? Where, we'll talk about the set of all X, where A is less than X is less than B, right? So notice A is not in this set, because A is not strictly less than X. When we talk about a picture of this, the way that we denote it is we say you have A, you have B, and we draw open circles. And that denotes that we're going all the way up to A, right? We're getting almost all the way there. If you're just a little bit less than A, you're in the set. But if you're at A, you're not, right? We could, of course, have sets that are open on one side, right? Like you could have something like this. We're open at A and we're closed at B, right? We will have the set X where just following these guidelines here, right? A is less than X is less than or equal to B, right? B is included, which is told to us by the soft bracket, and A is not, as the hard bracket shows. As a picture, you might have your A and your B. We don't include A, we do include B, and we're talking about everything in the middle. You can absolutely have infinite sets, right? Let's say talk about, let's include A, and we'll go all the way to infinity. This would be the set of all x, where x is greater than or equal to A, right? This is all of the numbers greater than or equal to A. As a picture, we might have A, we are including A, and we continue all the way to the right arbitrarily far. You could, of course, have, say, negative infinity to B. We'll use a soft bracket here. One thing of note, since infinity is not actually a number, right? It's just sort of this sort of process of going far enough or going arbitrarily far in some direction. Infinity always uses a soft bracket. For using negative infinity to B as a set, this is the set of x, where x is less than b. As a picture, we can drop down our line. We might have our b here. We are not including the endpoint, and we're going arbitrarily far to the left. If you were to say, talk about everything, negative infinity to infinity, well, that would be the whole set R, and it would be just the whole real line colored green. We can also talk about unions of intervals, right? Because intervals are sets, right? So we can maybe talk about the set -3, 1 union to 5. So this is the set of all x, where, let's see, x is between 3 and 1, or x is between 2 and 5. And what this looks like in our picture, right, we'll need all of the relevant points here. We'll need -3, we'll need 1, we'll need 2, and we'll need 5. So this is just, we're talking about both of these intervals at the same time, right? So we're inclusive on -3, we're open on 1, we're inclusive on 2, and inclusive on 5. We're talking about this interval and that interval. For intersections, we can proceed similarly, right? We might talk about the intersection of -3, 2, and we'll say 1, 5. What I want you to observe is the only places where these two sets overlap is actually the set 1, 2, right? So these two are equal. And so we can talk about the simpler version of this. Right? It's a set of all x, where x is between 1 and 2. If I draw my picture, you might see a little bit more of what I mean. So we have these same important points here. We have -3, 1, 2, and 5. Our first set, this one right here, this is talking about this set. And our second one, which I'll color in this sort of yellowy orange, which I don't actually know what to call that color. But this second one is closed on both sides, and it looks like this. So the intersection is all of the overlap. And that is this section right here. And that is closed on this side, right? Because notice that this point is included on both of them. But it's actually open on this side, right? Because while 2 is included in this set, it's not in the red set, so it needs to be open. Next, we're going to take a look at exponentiation. Again, this should be review for most of you, so we shouldn't need to spend too long on it. We're just going to introduce the concept and go over a couple of important rules that we want to keep in mind when we're using exponents. So an exponent is defined as such. We have some real number, a, and we're raising it to some power, n. And what this is we're taking a and we're multiplying it by itself n times. Right, so we have n of these. When we have an exponent, the bottom thing, a, this is our base, and n is our exponent. So we can do something like, let's say, minus 3 to the fourth, right? This is minus 3 times minus 3 times minus 3 times minus 3. We can break this up into this is 9 and this is 9, and 9 times 9 is 81. Fairly straightforward. But what happens when we combine them, right? What happens when we say a to the m, a to the n? When we multiply these together, right, we get a times itself n times, and then we get a times itself n times, right, where we'll denote that there are n of these, or m for the first one, and there are n of these. But what that means when we combine them all together is we have a times itself a bunch of times, but how many times is it, right? It's m, and then it's n. So it's m plus n times. So that's the same as doing a to the m plus n. And this is, in a lot of ways, the defining feature of exponents. That when you multiply two exponents with the same base, you add the exponent. Two other sort of important rules that we see is that for any real number a, where it's important to note that if a does not equal 0, then the following are always true, right? These are identities. We have that a to the 0 is 1, and we have that a to the negative 1 is 1 over a. These two rules, combined with this rule, can actually tell us everything we need to know about exponents. We're going to write down 6 laws for you right here, and these can actually all be proven just from this fact and these 2 facts. So here we have the laws of exponents. So these again hold no matter what, right? Number 1, we've already written it. We have a to the m, a to the n is a to the m plus n. An example of this, right, you might say that 3 squared times 3 to the 5th is 3 to the 7th. Or I'll write that 7 just a little bit nicer. Second, if we have a to the m divided by a to the n, well, this is the same as a to the m minus n, right? And that comes from this fact right here. Once again, say we have 3 to the 5th over 3 squared. That's the same as 3 cubed. Our third fact, and this is one that we will use a lot, say we have a to the m, and then we raise that to the n. Well, that is the same as doing a to the mn, right? When we raise to a power and then raise to a power, we multiply, right? Which could be the same as saying 3 squared, as an example, to the 5th is equal to 3 to the 10, right? 3 to the 2 times 5. Our fourth law is that, say we have 2 numbers a and b, and we raise those both to the nth power. That's the same as raising a to the nth power and b to the nth power and multiplying the 2 answers together. I'm going to move these examples over just a bit to give me more room. So let's say we're doing 3 times 4 squared. That's equal to 3 squared times 4 squared. Just like this goes into addition, it can also go into, say, division, right? Because division is just sort of fancy multiplication. So if you have a over b to the n, that's equal to a to the n over b to the n, right? This exponent kind of goes into our division. Finally, let's say we have a over b to the negative n, right? This just continues working with reciprocals, right? As we saw here, a to the negative 1 is 1 over a, right? And so we have a negative 1 here. And so that's the same as just saying b over a to the n, right? As an example of this, we'll say if you have 3 over 4 to the negative 2, that's the same as saying 4 over 3 squared. Now I know that that was a lot, so let's do some quick examples of this. Right, let's say if we have x to the 4th times, say, x to the 7th, that would be x to the 11, right? Because it's x to the 4 plus 7, and 4 plus 7 is 11. Okay, let's try our next one. Let's say what is 2a cubed b squared times 3ab to the 4th. And then let's take this last expression and cube it. Well, this one is a little bit more involved, but we can take it a piece at a time. First, let's analyze this. So we'll copy this original first one down to a cubed b squared. We can distribute this 3 into each of the terms. 3 cubed is 27. We have a cubed. And b to the 4th cubed is b to the 4 times 3, which is b to the 12. Now I'm just combining these via multiplication. 2 times 27 is 54. A cubed times a cubed is a to the 6th, right? Because when we have the same base and we're multiplying, we add the exponents. And then the same here, b squared times b to the 12th is b to the 14th. So most operations that we work with, right, they all have their inverses, right? Addition has subtraction, multiplication has division, and the inverse of the exponent is something called a radical. And you've seen a radical, right? The most common radical that you've seen, and it should be very familiar to you, is this one right here, the square root. And what this means is that if the square root of a equals b, if the square root of a equals b, well, that means that a is equal to b squared. We can actually define this for arbitrary radicals, right? We can say that the nth root is defined as such. If the nth root of a equals b, well, then a equals b to the n. Right, again, this should be fairly familiar. One small note to be aware of is that if n is even, well, then we have to restrict a and b to be greater than or equal to 0. Just as square roots of negative numbers fail in the real numbers, so do all of our even roots. We'll do 2 quick examples. Right, let's do the 4th root of 81. And we actually saw something like this earlier, right? We know that 3 to the 4th equals 81. So the 4th root of 81 is 3. Similarly, let's say take the cube root of negative 8. Sorry, sort of spoiled the answer there. The cube root of negative 8. So what times itself 3 times equals negative 8? Well, that's negative 2. Some quick properties of this, just as with the other ones, right? Or just as we looked at with exponents. So for our properties of radicals, we know the following identities to be true. And we will use these again sort of just throughout the quarter. Number one, if we're taking the nth root of a times b, well, that's the same as taking the nth root of a and then taking the nth root of b and multiplying them together. Two, just as with the last one, since division is just a fancy form of multiplication, if we're taking the nth root of a over b, well, that's simply the nth root of a divided by the nth root of b. This one's a little bit more interesting. If we nest them, right, so let's say the nth root of a of the mth root of a, sorry, the nth root of the mth root of a, well, that is the n times mth root of a, right? Just as before, when you multiply, or when you continue to raise exponents, you multiply. When you continue to take radicals, you can just multiply. Fourth, this one is sort of split into two parts. So first, if n is odd, well, if n is odd, then the nth root of a to the n is a, no matter what a is. However, if n is even, well, the nth root of a to the n is actually the absolute value of a, right? For example, right, because that may seem a little bit strange, let's say take the fourth root of negative 3 to the 4. As we saw before, the negative 3 to the 4 is 81, and the fourth root of 81 is 3. But by doing this raised to a power and then take that powered root, we actually end up taking away our negative 1 and being just left with this absolute value. We'll do two examples here really quick. We'll start. Let's say, let's find the fourth root of 81 x to the 8 y to the 4th. Well, as we saw with this rule here, we can break this up into individual pieces, right? The fourth root of 81, the fourth root of x to the 8, and the fourth root of y to the 4th. And so what we can do from here is we can actually, well, first we can write the fourth root of 81 as 3. We can write the fourth root of y to the 4th as the absolute value of y. But what we can do here is we can write this middle term as the fourth root of x to the 4th, of x squared to the 4th. But we know from the fact that that x squared is always positive, right? The absolute value of x squared is x squared. We don't actually need the absolute value bars on this term when we take the fourth root. So this is 3x squared times the absolute value of y. The final thing that we need to talk about before we can kind of move on and start sort of doing some pre-calculus are rational exponents, right? What happens when we raise a number to a rational exponent? Right? And the way that we're going to discover this, right, is let's say we do a to the first. Well, a to the first is a, but a to the first, 1 is equal to n over n. But then I can break this up, right? I can say that this is a to the 1 over n to the n. But what does it mean that when we take an object, raising it to the nth power and get a? Well, that means that a to the 1 over n is the nth root of a. And this is actually the natural extension of the rules that we've already looked at, right? Those rules that we said govern our idea of exponentiation. Well, it turns out that if we extend those past whole numbers, this is what we get, right? We'll sort of do one of our first big definitions. So for m over n in lowest terms, which means you can't simplify the fraction anymore, and m and n are integers, and n is greater than or equal to 0, a to the m over n is the nth root of a to the m, or, and these two definitions are totally equivalent, a to the m over n is the nth root of a to the m. Whereas before we qualify this if n is even, well, then a is greater than or equal to 0. And we can do a few quick examples of this because I know that may seem like a confusing definition, right? So let's start with something simple. Let's say 8 to the 2/3, right? You can break this up into whatever order you want. I'm going to take the cube root of 8 first and then square it, right? That's the same as 2 squared, which is 4. Getting slightly more complicated, right? We can say 2 a cubed b to the 4th, and let's raise that to the 3/2 power. Well, what we can do is we can distribute this in to each of our terms, and we'll get 2 to the 3/2, a to the 9/2, right, because we're multiplying, and b to the 12/2. Well, we can split this up and simplify this just a little bit, right? 2 to the 3/2 is 2 times the square root of 2, right? Because it's 2 times 2 to the 1/2. A to the 9/2, let's say we'll just keep that as a to the 9/2, and 12 divided by 2, b to the 6th. Let's do one more of these. Let's say the square root of x times the square root of x. Well, when we do this, we can sort of break this up into two components, right, as we saw in our exponent rules. This can be the square root of x times the square root of the square root of x, which, if we write these as fractional exponents, that's x to the 1/2 times x to the 1/4, right? Because remember, when we take double, this is the same as the 4th root of x. But now we have the same base and we're multiplying, so we need to add our exponents. So that's x to the 1/2 plus 1/4, so x to the 3/4.